Good morning, dear students. I am Dr. Batri Srinivas, Professor of Chemistry in St. Peter Engineering College. Today we are going to discuss about the splitting of d orbitals in tetrahedral complex. What is the topic? Splitting of d orbitals in tetrahedral complex and also octahedral complex. Two topics today we want to discuss. Okay, in the last video, what we have seen, we learned that d orbitals postulates crystal field theory containing the postulates and splitting of d orbitals. That is the postulates. So how it will. Then the splitting of d orbitals. So two sets splitting, axial and non-axial. Axial and non-axial orbitals. We have seen yesterday the loops dxy, dyz, dzx, dx square minus y square, dz square. That orbitals we described yesterday. Okay, today, now we will see the tetrahedral complex, splitting in the tetrahedral complex. Okay, tetrahedral complex means first we will see the tetrahedral structure. So what is the structure? This is the cube, this is the central metal, this is the y-axis, x-axis, z-axis, like that we take. This is central metal, y-axis, x-axis and z-axis. Three axes are there. And the ligand, four ligand approaches to the central metal atom to the four corners. Okay, so for alternative corners, this is the one corner and ligand. Okay, we take the other ligand, one corner, and leave this one, another corner. Alternative corners. Okay, now this is the alternative corners. So how many? 1, 2, 3, 4 alternative corners. This is the tetrahedral structure. Means tetrahedral geometry having the central metal atom. Tetrahedral geometry having the central metal atom and four ligands at the corners. See here in tetrahedral complex, the four ligands occupy the alternate corners. We know that of a cube. In the tetrahedral complex, the four ligands occupy alternate corners of cube and metal ions is placed in the center. The metal ion is placed in the center. Here the d orbitals are not pointed directly towards the ligand. However, calculation shows that the x, dxy, dyz and dxz, just before we have seen yesterday class, non-axial orbitals, dxy, dyz and dxz, non-axial. Or orbitals are close to ligands, then dz square, non-axial, axial orbital, dz square and x square minus y square. So therefore the axial and non-axial orbitals, here the degenerate orbitals, axial and non, all are same orbitals, all are equal energy, dx square, y square, dz square, axial and non-axial orbitals are having the same energy and split into two generate sets. Yesterday we know that two sets, easy set and T2. What are that? The degenerated orbitals split into two generate sets. One set consists of a lower energy, that is a dx, dyz and dxz. That is called the non-axial orbitals. And orbitals, the other orbitals mean having the higher energy orbitals. Higher energy. That is dz square, dx square, x square minus y square, dz square and x square minus y. These are the axial orbitals. So the energy of T2G orbitals mean triple generator orbitals. Orbitals are raised up and each orbital lowered from the center. That we can see in the diagram. Okay, that we can see in the diagram. Just carefully. So what are the two types of orbitals are there? Axial orbitals and non-axial orbitals. So two types of orbitals are there, axial and non-axial. One is the lower energy state, another one is the higher energy state. So T2G and EG orbital, double generator and triple generator. So that is we have to discuss in the diagram only. So that is description very well in the diagram. Okay, so what is the diagram? In the five orbitals are, that is the energy level diagram. We can say energy level diagrams. Five d orbitals. You have to take the 5d orbitals. 1, 2, 3, 4, 5. So that is the dxy, dyz, dxz, dx square minus y square and dz square. These are the 5 degenerated orbitals. Okay, 5 degenerated. Okay, so this is what energy level diagram. Okay, energy level diagram. Let's say energy level diagram. Now, when these d orbitals, when light-on approaches to the central metal atom, what happens? Just raised up. They are raised up. They are raised up directly. Okay, now these 5 orbitals in the crystal field. 1, 2, 3, 4, 5. So okay, this is the 5 orbital. So this is called, we are say, average energy of the d orbitals in the spherical crystal field. What is that? Average energy of the crystal field. Average. Crystal field. The crystal field. Splitting. Crystal field. Splitting. What crystal field? D orbitals in spherical crystal field. We can say spherical. Spherical crystal field. So far, average energy. First of all, when ligands approaches to the central metal atom, then simply the d orbitals, the degenerated d orbitals slowly raised up and then started to split into 2 sets. One is the T2G, another one is the EG. EG and T2G. So T2G, we know what are the 3 orbitals. 3 orbitals. Here 2 orbitals. What are the 2 orbitals? dx square minus y square and dz square. Here dxy, dxz and dyz. So two sets. Now the energy difference here, how much is there? This is the pericenter. And from pericenter to T2Z energy level, that is how much is there? The energy level. So delta T is the tetrahedral, so delta is the energy. How much? That is the 2 by 5. 2 by 5. Delta T value is the 2 by 5. Whereas here, delta T equal to 3 by 5. 3 by 5. Okay, the energy difference 2 by 5 delta T from pericenter. Here, so total is the total. So this is the diagram splitting of d orbitals in tetrahedral crystal fields. So how many? First of all, the dxy, dyz and dx square minus y square are raised up when ligands are approaches to the metal ligand, central metal atom, the d orbitals are raised up and in the average crystal field. In the crystal field, the splitting takes place. They are the Eg and 2Tg, Eg and T2G. Here, it has been observed that the energy separation between the Eg and T2G, 2Tg and Eg is smaller than the octahedral complex. We are going to discuss the octahedral complex also. So this is about the tetrahedral complex diagram. So just a diagram you have to remember. In the diagram, what is that? The orbitals. What are the orbitals? Degenerate orbital. Degenerate orbitals. First of all, when they are approaches to the metal ligand, so they are raised up in the crystal field. That is the average energy of the spherical crystal field. Then splitting takes place. There are the two sets of splitting. One is the 2Tg, another one is the Eg. So T2G is the dxy, dxz and dyz. And Eg, the dx square, y square, dx square minus y square and dz square. This is the two sets of d orbitals. Now the energy is the, from pericenter, delta T is equal to 2 by 5, the T2G energy, and Eg energy, the delta T is the 3 by 5. So T means tetrahedral complex. Okay, this is about the splitting of d orbital in tetrahedral complex. Now we can look the splitting of orbitals in octahedral complex. Splitting of d orbitals in octahedral complex. Just to write the octahedral complex. So it's very easy. If we can understand this tetrahedral complex, then we can understand just opposite of the tetrahedral complex. The diagram, so totally opposite. So mean here the complete, rotate it simply. This is the 2 by 5 mean 2 by 5, here 3 by 5. Okay. Here T2G, here Eg. So here only 2 orbitals, here the 3 orbitals. That is the dxy, dyz and dzx. dxy, dyz, dxy, dxz and dyz. Here dx square minus y square and dz square, two sets, the opposite of the, here in octahedral. Octahedral means square, octahedral complex. So when the ligand approaches to the central metal atom of the ligand along the axis only. So see, the diagram is this is the central metal atom. What is this? Central metal atom. So in octahedral complex, the ligand approaches to the central atom along the axis, mean like this, like this. These all axes. So z axis, y axis, z, y, x, all axes. Okay, all axes. So now here we can say that in octahedral complex, total how many axes are there here? So corners 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. Total 1, 2, 3, 4, 5, 6. 6 means 6 ligand approaches to the metal atom. 6 ligand. Just we write the ligand. 6 ligands. So when the octahedral complex, the ligands approaches to the central metal atom along the axis. How many? Total 6. As a result, the axial orbitals are what? dz square, dx square minus y square, axial orbitals, or experience greater repulsion than the non-axial orbitals. They have the greater repulsion. dz square and x square minus y square having the greater repulsion than the dxy, dyz and dxz. The degenerate orbital split into two generate sets. One consists of lower energy and more stable. That is what? dxy, dxz and dyz. This is having the more stable and low energy. And other set is the Eg orbital, that is the dz square and x square orbitals. So now the splitting of d orbitals, mean the splitting of degenerate orbitals under influence of the ligand is termed as a crystal field splitting, and the energy separation between them is denoted by the delta O. So we can write the not delta T, here delta. T mean tetrahedral, O mean octahedral. The splitting of degenerate orbitals under the influence of ligand in termed as a crystal field splitting, and the energy of separation between them is denoted by the delta O. Okay? Now here the energy of T2G orbitals is decreased by how much? T2G by 2 by 5. The energy of T2G orbital is decreased by the 2 by 5 delta O. And the energy of orbitals rises up by 3 by 5. Rised up. The delta O. How much of energy? 3 by 5 delta O. This is about the hypothetical degenerator. You can say hypothetical. So it is important to note that the crystal field splitting energy depends upon the field produced by the ligand. The crystal field splitting, especially the crystal field splitting produced by the ligand and the energy on the metal ion. When the ligands, this is a crystal field theory, when ligands are approached to the metal ion, they are produced on the metal ion, charge on the metal ion, produced by the ligand and the charge on the metal ion. So the ligand that produce strong field and causes are called the strong field ligand. The ligands are mean when the ligand approaches to the metal ion, the ligand that produces strong field and causes are called the strong field ligand, and those that produce weak field causes a small degree of splitting and are termed as weak field. Weak field and strong field. The two fields are here. Strong field depend upon the ligands. Depend upon the ligands. So what we have seen, just once again I will repeat this one, octahedral. So here this is the octahedral diagram, the d orbitals. When the ligands are approaches to the metal ion along the axis, so that degenerate orbitals are dxy, dyz, dxz, dx square minus y are raised up in the crystal field. And then started the splitting into two sets. That is, the one is EG set, another one is the T2G set. They are the dxy, dxz and dyz, having the energy is the 2 by 5, and another set is the EG set, dx square minus y square and dz square. So this is about the diagram and octahedral and tetrahedral we have completed. Just one diagram, if you know, just opposite of the another one, tetrahedrally completed. There the shape is the cube shape, here the octahedral geometry. This is the octahedral geometry. 4 corners. They are the alternate corners. The ligands are attached in the alternate corner. So just I will tell you the two differences. We must remember the differences. Of tetrahedral, just tetrahedral, octahedral. So what are the difference? The first one is the degenerate orbitals. Degenerate orbitals, same energy levels. Here also degenerate orbitals. Raised up, average. Here also raised up in the crystal, in the spherical crystal field. Spherical crystal field. Up to here safe. Then the third point is the here T2G raised up by 3 by 5 delta T. Here T2G raised by the 2 by 5 delta O. Here EG 2 by 5 delta T. Here EG 3 by 5. So non-axial orbitals, axial orbitals. EG set and EG set. Just these two are the exact opposite. You have to remember this one. One is the octahedral. And the structure here in tetrahedral, that is a cube-shaped structure. Central metal atom, Y, X, Z, alternate corner. Ligands are approaches alternate corner. Here that